Now I've changed the model a little bit. Most of the numbers are going to come out the same as before, but now let's say that instead of, and let's give it the temperature interpretation, instead of approaching a temperature of 0, let's say, and that would correspond to, we take this object, whatever it is, and set it in a room or set it outside when the temperature is 0 and is going to stay there. So the temperature is going to approach 0 in the way that we've illustrated here. Now this graph is going to change slightly, so the numbers here are going to change slightly. So I've taken out most of the numbers that are going to change, and I've written in a few different numbers. So in this case, let's say we're putting the thing not outside at 0 degrees, but we're putting it in a room where the temperature is 20 degrees. At 20 degrees, if I'm thinking Celsius, that's a relatively comfortable room. Probably going to wear, you're going to want to wear a shirt, maybe even a somewhat heavy shirt, maybe even a sweater. It's not totally terribly warm, maybe a little below 70 degrees Fahrenheit, but it's not bad. Okay, so in this case, what drives the temperature toward the room temperature is how far this thing is away from the room temperature. And how far is it away from the room temperature? Well, if the room temperature is 20 degrees, it's T minus 20 degrees from room temperature. So, for example, if the thing starts at 70 degrees, the object, and the room temperature is 20 degrees, the difference is 50 degrees, and that 50 degree difference is what drives the temperature change. Okay? So we're going to say, okay, now our rate of change is going to be big T minus 20, because now we're in a room at 20 degrees. Okay? And let's just, so the numbers don't have to change much, let's assume we have an initial temperature of 70 rather than 50. You could work it out for 50, but I'm going to work it out for 70. Okay? Now everything else is the same. So we're going to assume that T equals 0, little t is 0, time is 0 when temperature is 70. So, and there's one that I should have changed but didn't. Okay, so your temperature is 70 when the time is 0. Now we can do everything. We can predict the approximate change in T. We've got a rule for calculating that rate, so certainly we can calculate the rate of change of T and then apply that for a time interval of 0.4 time units. So if T is 70, then the rate is, of course, d big T, d little t. Well, that's going to be negative 0.5 T, and I kind of changed, I didn't change what I thought I'd changed here, so let's fix that. Okay, the rule then says that the rate of change of temperature with respect to time is going to be what? Negative 0.5 times big T minus 20, which is negative 0.5 times 70 minus 20. And 70 minus 20 is 50. Negative 0.5 times 50 is negative 0.25. Negative 25, sorry. Okay, so our rate is negative 25. We multiply that by 0.4, we get negative 10. So what's our new value of T? We take our old value of T and the value we started with, which was 70. To that we add negative 10 and we get negative, we get 60. And then little t still changes by 0.4, so it becomes 0.4. Started at 0, changed by 0.4, it goes to 0.4. So now the temperature is 60. T is 0.4. The next increment, the rate is what? Negative 0.5 times T minus 20, so that would be 60 minus 20. And 60 minus 20 is 40, and negative 0.5 times 40 is negative 20. So that delta T is rate times, delta big T is our rate times delta little t. That's going to be negative 20 times 0.4 or negative 8. Our new temperature is then going to be the temperature we started with, which is 60. We add negative 8 and we get 52. So our new time is 0.4 plus 0.4 equals 0.8 for the same reasons it was that before. So on our table, our big T is 70. Putting 70 into our new rule, well, we still get the same rate of change that we had previously. And our change in temperature is the same as it was previously, so our new temperature is 60. Now our new temperature is 60. Calculate the rate, we get this. Multiply the rate by the delta little t, we get negative 8, so we get 52. We increment our time, so now we have 52 here, etc. Okay, so the only difference now is going to be, since we originally started with a temperature 50 degrees above the room, but the room is at a higher temperature, all our temperatures are going to be 20 degrees higher than they were. The rates are still going to be the same because now the room is 20 degrees higher. So our graph, we would have T equals 70, and we would have our time axis down here, but now not everything is labeled. Well, our vertical axis isn't quite right anymore, so we're going to have to change our position of our horizontal axis, our time axis. We have to have a couple more 10-degree increments before we get down to T equals 0. But now, here's our graph. Now, I haven't labeled everything down here, but this is 0.4, this is 1.6, and so forth. Whereas before, our t-axis was here, and our temperature was approaching this t-axis as an asymptote, the temperature is still going to approach the same line, but that line is now not t equals 0, but it's our t equals 20 line. Okay, so think about what we're saying here. Now the bottom line, though, is this procedure works just as it did before, but we got a t minus 20. So this would be the rule that was written on one of your problems like this. For TR equals 20. In the given problem, all you have to do is identify TR and you have your rule. If I tell you what the temperature of the room is, there it is.